We're going to learn a new phrase today, and that phrase is shockingly z-score. What exactly is a z-score? Well, a z-score is on the normal curve or the bell curve, and it means what happens when you don't fall right on a perfect standard deviation. So what happens when, if I look at this example, I know my average is 62. I can figure out my standard deviation is obviously 3.2. Well, what happens if I am 64 inches? I'm somewhere between 1 standard deviation and 2 standard deviations above average, but I want to find out to the nearest hundredth where exactly I lie. This is the formula for a z-score. And yes, you are going to have to memorize that. It really makes sense if you think about it. Z, in other words, where you lie on the bell curve, is found by taking your score we subtract from it the average. So this way we can find out if you're above or below average. If your score minus average is positive, that means you're above average. If your score minus average gets you a negative, you're below average. So we take your score, we subtract how far away you are from average, and then we divide it by the standard deviation. There, that's your z-score. It'll point to you exactly where you lie on the graph. I'll tell you why in a minute, why it's called a z-score and not a L-score or an M-score. It kind of makes sense when you hear it. But let's talk about it and let's see what happens. So we have the boys' heights, and we're looking at 7th graders. It has to say normally distributed, whichever way you like to say it. Potato, potato, tomato, tomato. So once it says that it is a bell curve, then we can do our standard deviations. A mean height of 62, here it is. A standard deviation of 3.2. Find z-scores to the nearest hundredth for each of the following heights. So, okay, hey, I'm 66 inches. So 66 inches tells me I am right about there. So I'm above average. How far am I above average? How many standard deviations? I'm 1 and a little more. Well, let's just do some easy math here. I'm 66 minus 62 divided by 3.2. So I'm 4 divided by 3.2. I can see that I'm plus, that I'm above. I can see that 4 divided by 3 is I'm bigger than 1, so I'm more than 1 standard deviation away. And if I just do the math, I'm 1 1/4 standard deviations away. How about 57 inches? Well, we always start with the data. We subtract the average. Uh-oh, this kid's below average because 57 is below 62. And we divide it by 3.2. So that is -5 divided by 3.2. And -1.56, but we said we were going to go to the nearest hundredth, so it's going to be -1.56. And it's going to be approximately. So we're 1 standard deviation and a half below. So if I had to estimate that, here's 1 standard deviation below, and halfway would be right about in there. And 70 inches. Wow, this kid's really above average. This is a tall dude. 70 minus 62 divided by 3.2. Okay, so that's 8 divided by 3.2. He's not quite 2 standard deviations above. Well, I don't need to do my calculator really. I can do 80 over 32. 8 goes in there 10 times. 8 goes in there 4 times. 2 goes in there 5 times. 2 goes in there twice. So he's 2.5 standard deviations above average. 1, 2.5. That dude's way out there, which we can see anyway because that's where 70 is on the bell curve. All right, so I'm going to come back here and I'm going to clean this up. I'm going to get rid of all my writing. And why is it called clearing from page? Why is it called a z-score? Because z stands for 0. We're looking at 62 as, oh, here's that word again, ground zero. Then where are you in relation to the mean, to the average? We said a plus would mean you're above, below would mean minus, and then we just figure out how far you are above and below average via standard deviation measurements. So we can run through these really quickly. Here we are with the standardized test again. Normally distributed, so we know we're on a bell curve, with a mean of 560 and a standard deviation this time of 75. So yesterday we did kind of the same thing, but we had a standard deviation of 80. So I've already taken the time and I've already made my bell curve here. I always like to draw my bell curve. You don't have to, but I love the visual. Find the probability. Ooh, probability. That means we're looking at a percentage, part of this bell curve, that a test picked at random would have a score larger than 720. So that means my lower bound is 720. And wait, there is no upper bound. Okay, so this is why I like my bell curve. I'm going to come over here. 720 is right about there. So what's the probability that I would have a score larger than 720? Well, this is going back to my distribution. And my lower bound is 720. My upper bound is really large number. My average is 560. And my standard deviation is 75. Voila. Round to the nearest tenth of a percent. So if I move that decimal over 1, 2, it's 1.6%. So based on this, only 1.6% is the probability that somebody scored higher than a 720. Now, you may look at me and go, hey, that's kind of the same as yesterday's. Well, you can do this another way. We could do this via z-scores. We could have said, all right, 720 minus 560 divided by 75. All right, so that gets me 160 over 75. And I'm going to be lazy and do 160 divided by 75 on my calculator. I'm going to get a z-score of 2.1333. Now, I didn't say where to round my z-score. When I come over here to distribution, but this time, I'm going to use z-scores to figure it out. So I want my lower bound to be that 2.133333 z-score. I want my upper bound to be a large z-score. My average is 0. Get it? Z-score, 0. My standard deviation is 1. So now I can use this when I don't know what the standard deviation is, but I am talking about z-scores. It's going to be very powerful. There I go. I get the same answer, 1.6%. So I could do all of these questions either way. I could use the actual numbers or I could use their corresponding z-scores. Most of the time you can use either one. Sometimes the problem is worded where you have to use one or the other. For example, The average weight of a full-grown beef cow is 1,470 pounds. I haven't read these questions since last year. They amuse me. With a standard deviation of 230 pounds. If the weights are normally distributed, they always have to say that, we know we're on a bell curve, what is the percentile of a cow who weighs 1,750 pounds? Well, we could do this by a z-score. So we could say 1,750 minus 1,470 divided by 230 is 1.22. We could come here and we could do that out. We can say, okay, what do we want to do? What's the percentile of a cow that weighs 1,750 pounds? So its lower bound is we don't know what, large number, made it up. Its upper bound is 1,750. We could say its average is 1,470. We could say its standard deviation is 230. And we can get as an answer roughly 88.8%. We could do that by z-score. I could come in here. I can say we don't know our lower z-score. We know our upper z-score is 1.22. We know our average is 0, z. We know our standard deviation will be 1. And there we are again. A little different. Off just a little. And that's because we did some rounding here. But I want you to come over here. And when I was in school, and we didn't have this, we had to use tables. This is a normal distribution based on a z-value. You have this in your packet. So basically, this is what I would do. I'd come down here, and the first thing I would check is, what kind of z-score is this? This is something that gives me the area from the mean to my z-score. So my z-score for this cow was 1.22. So I would look here and I would say, whoops, 1.22, I think that's 2 right there. Yep, is 0.3888. Now remember, if I took my normal distribution, there's my mean, here is my cow at 1.22, they told me this is 0.3888. Do you see how I got 88.8%? That's right, I have to now add on 50%. When I add those two together, I get 88.8% again. There's all types of z-tables, and you have to be careful which one you do. Cumulative z-table. See, now the cumulative one tells you how far it is from the bottom all the way to your z-score. So my z-score was 1.22, and notice when I go here to 1.22, look at that, 88.88. So be careful if given a chart how to read it.